Howdy guys, welcome to the first video of many that I'll be recording. In this video what we're going to be doing is we're going to be kind of summarizing some of the things that you watched in the previous 3 videos, and I'll be giving you a few more hints and tips as to how to make sense of what you've been watching. If you have any questions, then feel free to post them in the discussion board below. And I'll try to get back to you as quickly as I'm able to. Also, for the end of this particular lecture video, you will understand, hopefully, the joke behind my shirt here. And hopefully you'll get it. Okay, so let's get started. First thing that I want to do is I want to introduce to you all some more vector terminology. This is very important because, as you've probably noted from the videos above, we have to think in 3 dimensions in order to explain what we're seeing with these magnetic forces that act on charged particles and currents as they move through a magnetic field. So, first thing I'm going to point out to you is, in order to help us think in 3 dimensions, we have a problem in that we draw on a 2-dimensional surface. Okay, so we draw our vectors like this, and we can break them up into components like so and like this. But what do you do? How do you draw a vector if it's coming out of the board towards you or going in the opposite direction this way? Okay, good question. Here's the terminology that we use to make that work. If there's a vector that's coming out of the board towards you, like this, we represent that as a circle with a dot. If instead of a vector coming out, you have a vector going into the board away from you, we represent that with a circle that has an X inside of it. Now, sometimes people have a hard time remembering which is which, so I'll give you a couple of ways to think of this. One way I like to think of it is, imagine that you're firing an arrow out of a bow, right? If you happen to be the unfortunate recipient of said arrow, the arrow tip is at the end and it's coming out towards you. However, if you are the person firing the arrow, then the arrow is moving away from you. So what you see is the feathering or the fletching of the arrow as it moves away from you. Another, perhaps more humorous way of thinking of this is something that a student said years ago. They said, "Oh, just think of a belly button. A belly button. This is an innie, and that's an outie. Whichever works for you, great, go for it." Okay, so this is the terminology that we have to use to think about vectors in 3 dimensions, as opposed to simply 2 dimensions. Okay, and so let's summarize some of the things that you observed in the videos above, specifically the video with the electron beam in the magnetic field. Okay, so let's erase this. Okay, so what you saw in those videos above is that you had 3 things. You had a charged particle that was moving, either in the form of an electron beam or a conventional current through a wire. You had a magnetic field, and you also had a force of interaction between those 2 things. And those 3 things are at right angles to each other. Okay? And so we need to have a, pardon the pun, handy rule to help us understand how all of this works. Okay? And we have just such a trick. I'm wearing it right here. It's called the right-hand rule. or the left-hand roll, depending upon if you're talking about a positive or a negative charge. And so let me write a couple of things up here, and then what I'll do is I'll show you how this trick works, or how I like to do the trick. Okay, so first thing to note is that when you are talking about charged particles moving, you use the right hand for positive charge, and you use the left hand for negative charge. Okay. Now, I don't know about you, but when I was a student, I had a heck of a time remembering that. And so I'm going to show you guys a neat little trick to help you all remember it. Feel free to use this. But don't do this on the AP exam. If you're taking the AP exam, don't do this. But up until that point, that's fine. What I did when I was a student is to help me remember this. I literally wrote on my palm positive and negative signs so that I remember. Right hand positive, left hand negative. Now, an interesting question is what happens if you're talking about neutrally charged particles, such as a neutron or a neutrino. I'll get to that in a second. Okay, but as far as right hand positive, left hand negative, what do the different parts of the hand do? Okay, here's how it works. Your thumb represents the direction that the charged particle or the current is moving. Your fingers represent the magnetic field lines. That represents the direction the magnetic field lines point. And remember, magnetic fields point from north to south, okay? Coming out of north poles, going into south poles. And then your palm pushes. Your palm pushes because a push is a force. Okay, let me summarize that on the board here. Now I'm going to label each one of these with a vector quantity so that you're very clear, because sometimes people mess up what's a field, what's a force, and so on. So let's be very clear about that. What we mean by motion of charges usually is velocity or current. So I'm going to label that with, this is a velocity vector or current vector. The fingers are the magnetic field, and the symbol we use for magnetic field is a capital B vector. And the palm is a force, and that's different from the field. Okay, the force is a push, and so what we're talking about there is F vector. Okay, so thumb, direction the charge moves, or the direction the current moves. Fingers, magnetic field vector. Palm is a push. That's a force. And if you're talking about positively charged particles, use the right hand. If you're talking about negatively charged particles, use the left hand. Okay, what about neutrally charged particles, such as neutrons and neutrinos? Here's a great way to think of it. When we talk about neutrally charged particles have equal amounts of positive and negative. Okay, so let's suppose that what you've got is you've got a neutron, say, that's moving through a magnetic field. And you can think of it as the positive parts of the neutron will feel a force in one direction, as indicated by my palm here, pointing, say, in that direction. And the negative parts will feel a force in the opposite direction because the particles sticking together in the same magnetic field. So I got to line my thumbs and I got to line my fingers. And if I do that, my palms face each other. And if my palms face each other, then what's the net force? Zero. Right. No net force. So neutrally charged particles don't feel any force whatsoever as they pass through a magnetic field for that reason. Okay. Now, what we're going to do next is I'm going to go through a series of quick little exercises to make sure that you have a deeper understanding and you can apply this idea of the right hand and left hand rule. And then I'm going to pose a little question to you. It's a little something to make you go, Okay? All right. So suppose that what we have is we have a vacuum tube, kind of like what you saw in one of the videos above. And let's suppose that this vacuum tube has an electron beam passing through it, just like you saw in the video. And what we're going to do is we're going to imagine, all right, what happens if we bring a magnet close by and see if we can predict which way the beam is going to turn based upon our right hand and our left hand rules. Okay, so let's suppose I draw out my tube like this. Let's suppose we'll call this end of the tube the negative end. We'll call that end of the tube the positive end, right? So we have a negative electron, we have a positive electrode. And if I drive an electron beam through this, of course, the electron beam is going to go from negative to positive, okay? And I will represent the electron beam as a green beam. So the green represents the electron flow. Okay, so we've got our electrons moving left to right, negative to positive. Now, if we have electrons going this way, then we have a hypothetical conventional current going in the opposite direction, right? Okay, so let's mark that with a red marker. And I'll mark that with I, put a little plus on there to remind ourselves that it's conventional current. Now let's suppose that what I do is I bring a magnet into the mix here, okay? And let's suppose that what I do is I have the north pole of the magnet facing into the board this way. Now remember, magnetic fields come out of north, right? So if, for example, this blue marker, if the blue end here represents the north pole, then in this orientation, the magnetic field is going up this way. So if I point it this way, think for a second, which way is the magnetic field going? Give you a second to think about it. You can pause the video if you want to figure it out. Okay, the answer is the magnetic field is going into the board. And we represent that with a circle and an X, right? Any goes into the board. Okay, so we have a magnetic field going this way. And remember, the symbol for magnetic field is capital B. Okay, so let's use our left hand and our right hand rules to figure out what's going to happen to the beam. Start with the electrons, because the electrons are actually what's moving. Okay, so you have the electrons going in this direction. Okay, so we use our left hand for negative charge. We're going to stick our thumb in that direction. Now, remember, the fingers represent the magnetic field, so which way do the fingers have to go? They have to go into the board, right? So what you have to do is you have to turn your hand like this, right? So this will be a little bit awkward. And so thumb goes this way, fingers go this way, palm faces which way? Down, right? So that means there's a downward force that's going to act on the electron beam, right? So we would expect to see it bend downward as a result. So we'll mark that right there. Oops. There we go. Okay, now, you should confirm that, right? Go back to the video up above and confirm that that's accurate, okay? And you'll see that it is. Now, we can also think about it in terms of the conventional current, the positive charge flow. So if you want to do that real quick, use your right hand. Same rules apply, it's just with the right hand now. Thumb is the direction that the conventional current goes. Well, that's this way, right? So when we come over here, that's in this direction now. Okay, your fingers still represent the magnetic field, so your fingers go into the board again. And which way does your palm face? Down again. Okay, so it's consistent whether you use the left hand or the right hand. Okay, and that's important that things are consistent. So left hand, down, right hand, get my elbow out of the way, down, and it works. Okay, now let's do another one. If we flip the magnet around, right? So instead of my magnet, right, my North Pole going in, what happens if my North Pole comes out? See if you can figure it out real quick. Pause the video, I'll give you a moment to figure it out. Okay, now, here's what happens. If you flip the magnetic field around but everything else stays the same, the force reverses. Here's why. Let's go right up here and we'll flip the magnetic field around. If you have the North Pole magnet facing out this way, that means the magnetic field's coming out towards you. That's an outie. And so if you use your left-hand rule, say, for the electrons are still moving that way. Fingers now come out towards you, and the palm faces up, so the force reverses direction. Okay? Now, again, check it with the video above, and you'll see that if they reverse the magnetic field, you'll also see the beam curve upwards like that. Okay, you can do the same. You can do it with the right-hand rule as well, right? So if you use the right-hand rule, the current's going this way, fingers come out here towards you. Right? So thumb this way, fingers come out towards you like that. Palm faces up, right? Force is up again. Okay, nice and consistent. Okay, let's look at a couple others real quick. Let's suppose that what we do is we take our magnet, or North Pole, and we have the North Pole facing down like this. So the magnetic field is going to be going which way in that case? Downwards. Okay. So we have a downward magnetic field like this. All right, let's see which way the force is going to go. Okay, so let's start with the electrons because that's what's actually moving. That is what's actually moving. All right, got the electrons going this way. You've got the magnetic field going down. Which way does your palm face? Comes out like this, right? So that means that the force is coming out of the board towards you, like that. Okay? If you do the check, you check on your own with the right-hand rule with the current, and you'll see that it's consistent. If you take the magnet and you flip it over, instead of like this, right, when the field's coming down, you flip it this way, so the North Pole's up here, and the field is going up, then just like we saw before, to stay consistent, you will see that by flipping the magnetic field, use the left-hand rule again, flipping the magnetic field, the fingers go up, and your palm is facing into the board now, okay, away from you. And so now we're going to get a circle with an X for the force, like that. And again, check it with the right-hand rule, and you should get consistent results. You can also check both of those in the video above and see that that's what's actually going on. All right, last but not least, what happens if you take your magnet, remember, North Pole is the blue part, what happens if you orient it this way or this way, right? Where the magnetic field is going parallel to the directions that the charges are moving. Okay, well, as you can see from the video above, you see that nothing happens, right? You don't get any deviation of the beam whatsoever. It ends up that there's no force. But here's a way you can think about this with the left hand and the right hand rule. Okay, let's start off thinking about the electrons, for example. Okay, so if I get rid of my arrow here, and let's suppose that what we do is we orient our North Pole of our magnet going this way, so the magnetic field is pointing to the in this direction. Okay, if I do that, and if I use my left hand, what I can do is I can take my left hand, right, and correct, not right, left, and I can take my thumb and put it in the direction the electrons are moving. But I take my fingers and they go in the same direction because that's the way the magnetic field's going. And then what happens? My whole hand closes up like that. If my hand closes up, I have no palm. And if I have no palm, I have no force. Okay? force equals 0. Okay. Now, I can also think about what would happen if I have the magnetic field going in the opposite direction. Right? Suppose I orient it like this. Then if I do that, then I can think of looking at things in terms of the conventional current. Right? I can use my right hand, and if I put my thumb in this direction, because the conventional current's going the opposite way from the electrons, if I put my thumb in this direction, my fingers go in the same direction, because that's the way the field's oriented now, again, my palm closes up. And so if my palm closes up, I've got no force. Right? So the basic idea is that if you have a situation where the magnetic field is parallel to the direction the charge is moving, there's no deviation of the beam. Okay, so now, all of that said, let me ask you a little question that'll make you go, and think about it, and next time we'll address it. Okay, because all of this, everything we're talking about today, is just thinking about the direction of these forces when you have charged particles or currents moving through a magnetic field. But we'll have to address questions about, well, what's the magnitude? How do you calculate the amount of these forces based upon the amount of charge, how fast it's moving, what's the magnetic field strength, what's the current, all of that stuff. Think about this one. Let's suppose that we have the following scenario. Suppose I take a positively charged particle, such as a proton or a positron, and suppose that it moves through a magnetic field in the following way. Let's suppose it's moving in that direction at a certain velocity. And let's suppose the magnetic field through which it's moving is oriented in this direction. And we'll put a little angle between these two vectors. We'll call that angle theta. So here's the question. Number one, is there a force that acts on this positive charge? And number two, if there is a force that acts on this positive charge, in which direction is it going? Think about that. We'll see you next time. Go Team Physics.